All right, guys. Thank you very much, Dell, for the intro. My name is Ian Hutt. So I've been an electrical engineer working in power for about 15 years, and the past 5 years been doing a lot of work in the renewable space for solar, wind, and for especially battery energy storage systems and microgrids. I've been doing arc flash studies for various applications all over the industry for the entirety of my career. And I have a background in planning and system protection.
Hi, my name is Chris Nelson. I've been working in power for maybe a little bit over a decade. Kind of like Ian, I've been working in the battery space and the renewables pretty much since the batteries started taking off and getting popular. We've done quite a few projects. I started out working with relay settings and kind of moved a little more towards planning and other types of studies. So I guess the first thing I was hoping to talk about was just what is arc flash in general. And this will be brief because it's not the focus. It's more a focus on battery. But arc flash is it's an arc resulting from an electrical fault. They can make extreme heat, and that extreme heat leads to explosions because the heat has to go, or the expanding air has to go somewhere. The danger zone from these can be anywhere from a couple of feet to a couple of dozen feet, depending on how much fault current there is. Most of the calculation for these danger zones are from IEEE 1584. In general, the incident energy is a function of current and time, so I squared T. I believe we have a poll question coming up here.
And we'll wait about 30 seconds to give people a chance to respond, and then we will close the poll and we will share the results. Thank you all for participating. About 3 seconds left. Okay. And we're going to close the poll here, and I will share the results. Again, 5 being very experienced and 1 being not experienced at all. Looks like we have a mixed group with most folks being the less experienced category. Okay.
As I said before, we were hoping to focus on specifically battery arc flash for BESS systems. So what makes that different than regular arc flash? Number one, lithium batteries they're kind of the standard anymore, and they have just a very high energy density in them in general. And then we usually hook up a lot of parallel strings to get the desired voltage. So that makes the fault current just incredibly high. If anybody's worked on AC short circuit calculations, anything over say 30 to 50 kA is considered extreme. We've seen over 150 kA. So it's hard to get the equipment that's rated that high, and a lot of the time we have to negotiate with manufacturers to get them to rate them higher than they've ever tested them before. If we have a central inverter where a lot of strings are hooked up to one large inverter instead of a bunch of small inverters, that makes it significantly worse too. For the AC side, the highest arc flash is usually at the transformer low side and the inverter terminals. Quite often these come on a skid together, and you can't really separate them. Usually you won't work on that location, but if you ever have to, the arc flash is going to be extreme. They usually specify the protection for these transformers, the fuses, to save the transformer, not to save the people. So sometimes there's not much we can do about that. We'll try to specify different fuses, but sometimes they're already in the field and they can't even be gotten to change them. So sometimes the arc flash can be 50 to 80 cals at the terminals. We usually try to get it below about 30, but sometimes it's not possible. The other issue with lithium batteries is if you de-energize them, if you discharge them past a certain amount, I don't remember exactly what that is, maybe 20%, it ruins them. So you really can never work on these systems de-energized. It's also very low mobility because it'll be a lot of batteries inside. It resembles a shipping container a lot of the time, and there's just no escape if you're in there with it. So we try to take that into account when we do our studies. For the AC calculation, for low voltage, we usually use IEEE 1584 to calculate it. There's several methods for medium voltage, which is considered anything above 15 kV. The Lee method used to be the standard, but it tends to give inflated values. Sometimes that's less of an issue because it's the low side that the arc flash is bad on, but we try to use the other methods to give a little more realistic values. For DC, the main formula to calculate arc flash is NFPA 70E. So we'll take the short circuit current from ETAP or some other program like it, and then we'll either run arc flash inside that or we'll calculate it ourselves in a spreadsheet. The other way we can look at it is if the DC arc flash is too high, we can do a transient analysis of it, where we basically look to see how high or how fast the fault current rises, and if the fuse blows before the fault current is even at its highest, we can get a better result. We have another poll question.
Next one is, do you work with arc flash on your projects? About 20 seconds left. We're kind of balancing on that 60-40 percentage right now. See how things end up. Okay, about 77% of our attendees have voted, and with that, we'll close the poll. And here are the results. All right, with 54% saying that they do work with arc flash on their projects.
So significant amount, but not everybody. So I wanted to go over some of the typical hazard levels at some of our sites we looked at. We put in a very large battery system in West Texas. This one had about 20. This was not a central inverter. This had about 22.5 megawatt inverters. And sometimes the arc flash is worse if you raise the hourly capacity to like an 8-hour battery, but this one was 2 hours. And even with that, it was still incredibly high fault currents on the DC side just because of the size of it. So we were seeing 173 KA at the inverter on the DC side, and the fuses that had to break that current were seeing about 86 or 87 KA. It's just hard to find fuses that can even handle that. But we worked with the manufacturers, and I think we got them uprated so that they could. There's a number of things we can do to try to help the high fault currents and the high arc flash. The easiest way is if we get in early and we can help specify the equipment and the design. If we can't get in early enough in the process to do that, we can still look for strategies to reduce it later, but sometimes it might be a little bit of a redesign, and it could be more painful if you don't do the studies in advance. Doing the studies in advance also has the same problem of getting the equipment or getting the information to do the studies, because it doesn't exist yet. You're trying to get the specifications from manufacturers to do the studies. So there's a little bit of a chicken and the egg thing there. But if if it's already done and halfway built or the equipment's already specified, sometimes we can do the transient analysis I was talking about a minute ago. So we used current limiting fuses to just try to lower the fault current before, or try to shut down the fault current before it rises all the way. Instead of the steady state maximum fault current, we would see maybe half of that or a little bit less, depending, sometimes significantly less. But for DC, that fault current rise time, it depends entirely on the circuit and the inductance. So it's going to be completely specific to each site. So here is a printout of the DC short circuit current at that West Texas battery I was talking about. So up here at the inverters, it's incredibly high fault current at 173 kA. But if you look at the actual arc flash time, these fuses are incredibly fast. So the arc flash wouldn't have been very high here. Also down in the middle, I'm seeing about 118 kA there. The arc flash would not be significantly bad there either because all these fuses are so fast. Where it gets a little bit worse down below, just above the batteries, there's only 10 kA coming from that battery, but that battery doesn't have anything to trip it off with. There's no current limiting device there at all. So we would calculate that at 2 seconds, and the arc flash, it can be moderate or it can be significant there depending on just how much current is coming through. But the current from all the other batteries would be shut down much faster. So you're really only seeing the current from that one battery contributing to that 2 second arc flash time. I was hoping to show a little bit in ETAP on both the AC and the DC short circuit and arc flash a little bit too.
Mhm.
So this is that West Texas battery system. So it's incredibly large. There's just a lot of different inverters here. So this is the AC model. So at the high voltage, the arc flash is actually worse than I expected it to be. This is about 85 cals here. Oops. So
Yeah,
likely,
note that that's Lee method. So generally, it's going to be a very conservative result, right?
it
So
would be much less than that.
yeah.
But there's a fuse here and a fuse here. These are both the transformer fuses on the high side. It's not very bad right here at the high side of the transformer, just because these two fuses will take that down. Whatever protection is up here for the relaying for the utility, that could lower this 86 cals too, even if it is a little inflated from the Lee method. Down here at the low side of the transformer, it's showing 100 cals here, and that's incredibly significant, and it could be lowered by changing these fuses, but it could be that that's what you have to live with. I would assume you could change these fuses and lower it, because this fuse, I think when I looked at it, it was a 70 amp fuse, and I'm seeing this is arcing current, so the actual bolted fault current would be about 60 amps. I don't think these fuses are doing anything to lower this. That's why we get a 2 second fault clearing time for the low side. So those fuses could maybe be changed, and this model might have been updated since I got a copy of it, so it could be that we did do some mitigation there. So I'm gonna load the DC one line just to show that off a little bit too. All right, so this is actually a different battery because I was a different battery system because I was having some trouble getting the other one to load in my computer. It's a little bit of an older model, and there's some issues with the libraries. I think I'm running a newer version of ETAP than that one was. So this is using ETAP to run the arc flash on the DC system. And we don't always use ETAP for this because sometimes it's hard to get exactly what you want out of it. It takes a minute to run. So at the inverter, I'm seeing about 4 cals right here because of those incredibly fast fuses. I think we actually got a little bit less when we calculated it with our spreadsheet, but it's still 4 cals is not hard to live with. Down here, a little bit closer to the battery itself, I see about 3 cal. That's still not bad. So let me fault the bus down here and see what it is at the battery. So again, at the battery, there's no protection here. So we get 2-second fault clearing time, and ETAP is showing 1,000 cals here, which is not realistic. Likely what's happening is ETAP's taking the 5K from the battery and the 35K from the other batteries and just adding it up to 2 seconds. In our spreadsheet, what we would have done is take this 35 Ka of fault, we would have run that at the time that these fuses take to clear and got the arc flash from that side, which would be probably negligible. It'd be under 1 cal. And then we'd run this 5 Ka for the 2 seconds to see what that is, and then add the two numbers up. And this number would dominate that, and it would probably be somewhere around 30 to 60 cal. So that's kind of why we don't always use these or use ETAP to do this, because it's just harder to get it to do what you want. I think it might be possible to make it do that, but you have to tweak a lot of things, and sometimes it's easier just to do the hand calcs. So for mitigation for some of those high arc flash values, we can use faster DC or faster fuses for both the DC and the AC side. For DC, sometimes we need to do a transient analysis to see if they're actually faster and decide what to do about them, because we use steady state fault currents for the normal analysis. Another method we can do, it's kind of a last resort, but we can make longer cables. That will lower the arc flash current because there's more resistance, but more resistance makes more losses, and nobody really wants to do that. Earlier in the design, we can specify different inverters. We can have several smaller inverters instead of larger ones. We can have a DC voltage that's a little bit higher. All those things will help a little bit. So some of the protection we can use on AC, relaying and breakers, there are no relays and breakers that can handle this type of fault current and the speed we need to trip on the DC side. The fast burn fuses are really what we need to use on the DC side, and they are significantly faster than AC fuses ever could hope to be. So our time constant on the AC side is usually in the milliseconds, and DC side it'll be in the microseconds. And on the right, this is the specification of one of the fuses we've used. Where is the, the L over R is 0.5 milliseconds. So that's pretty fast. That's 500 microseconds at this fuse.
So so Chris, thanks for the intro on the steady state. Very good presentation. So I think what we want to kind of talk about now is we're going to get into the DC and the transient analysis portion. So if we're getting into the DC world and we're seeing fault currents and arc flash times that don't work for our project, we're basing all that on this idea of prospective fault current. So if the fault's allowed to persist and the fuse does not clear the fault by the time the fault gets to its total fault current, total available fault current, that's where that steady state analysis is very useful. But just like Chris was saying here moments ago, is that the DC fuses can operate very, very, very quickly, and it's hard just to put that into scale. So for most of us that work in the AC world, we're used to fuses that trip in the order of cycles, right? So a fast fuse may trip for a very high fault current in a cycle, maybe a couple of cycles. In the DC world, we're talking about fuse times that can be a 32nd or a 64th of a cycle. if we're thinking in that cycle terminology, you know, from the AC world. So that's where Chris was going with that, the 500 microsecond constants. Chris, can you back up a slide real quick?
Yeah.
So just to kind of put this in perspective, a lot of AC fuses and AC devices, even if the fuse is rated for DC operation, they're going to have time constants that are in the 10 to 15 millisecond time range. And now we're talking, you know, cycle time range, which is what we're typically used to in AC systems. But what I think the point that we were trying to make is that for BESS specific, especially for the lithium-ion technology BESS, which is predominant right now, that specific fuses have to be selected that have time constants that are appropriate to these types of projects. And we need those time constants to be in that 500 microsecond range. Just incredibly fast fuses that can help us with both short circuit problems and arc flash problems in the DC networks of batteries. So if you want to move the slide there, yeah. So here is a list. I mean, Commonwealth is an engineering consultant. We have no connection with any of these manufacturers. I'm just listing out a few of the ones that we have found through our projects and our research. Just these are some of the available market devices that are out there. We expect this list to be growing, and we expect new models from these manufacturers as time passes. But these are some of the ratings on some of these DC fuses that we have seen out in the network, or not in the network, in the market. So the one thing I want to mention is if you look generally for DC fuses, you're going to find DC fuses that are used in AC applications as well with time constants in that 10 to 15 millisecond range, and those aren't likely going to work for your application. These fuses here are built for battery energy storage systems by these manufacturers. They generally have L over R constants that are, you know, somewhere in the 500 microsecond to 1 millisecond ranges, which are more appropriate. And you'll also see some of the DC ratings be much higher. So as Chris mentioned with the steady state analysis, we're seeing DC fault currents at almost every location in the DC circuit that's over 80 kA. And most of these DC fuses that you find generally in the market have 50 kA ratings DC. So they won't work. With this list here, we show some examples of devices that have ratings that are over 50 kA, some as high as 250 kA. All right, so next up we have a poll question. Del, take it away.
All right, we have rate your experience with current limiting fuses. 5 very experienced, 1 not experienced at all. Please select one of the following. See where we are at. We got about 15 seconds left. Just as a reminder, the question box is open, so feel free to put in your questions and we'll get to those at the end of the presentation. Okay, with 79% of attendees voting, we are going to close the poll here and share the results with about 30% coming in at right in the middle, 28% not very experienced. So that's where we are at today. And away we go. Thank you.
All right, thank you, Del. So this would be a good slide here. So for those that aren't very experienced with current limiting fuses, first we'll talk a little bit about how they work in the AC world, because that's where most of us live. And for a current limiting fuse in the AC world, your AC rises are generally going to be very similar. You know, we run on a 60 hertz system in the United States, and you can all the fuse manufacturers that are building current limiting fuses kind of understand that and build fuse times that are appropriate to that scale. So over here on the right, we have a nice graphic from Littelfuse that kind of shows how a typical AC current limiting fuse would operate. So the idea behind a current limiting fuse is that you have a total prospective fault current that can be much higher than when the fuse will blow, and the fuse will blow before you ever get to that prospective fault current by having that fuse be faster than the AC rise. Now, if you guys look closely on this graphic, you'll see there's a red line that's running very close to the current y-axis. that is more indicative of what a DC circuit rise is going to look like compared to an AC waveform rise. So just to kind of give you a visual on how much faster a DC circuit is going to rise to its prospective fault current, it can be much, much faster than a typical AC waveform. So just kind of a good graphic to kind of put it in perspective about the differences of what we're talking about. You want to flip screens here? Next slide. All right. So when you're working with current limiting fuses in the AC world, because the AC frequency is kind of set and we know what those AC rises are going to look like, and we typically work with generally a relatively static range of maximum AC fault currents, that you have charts like this. This is a nice chart provided by Busman, and this allows you to compare. So if I have an application with such a fault current and I apply this fuse, I can tell what the maximum fault current allowed through that fuse will be. And this makes the analysis of current limiting fuses quite straightforward and simple. So this is very nice when working with current limiting fuses in the AC world. And there's a lot of times where this makes a lot of sense. So for example, say I have an application where I have a breaker, and on my breaker, I'd rather use a lower rating breaker because it's much less expensive, or I can get those breakers. You know, in today's world where supply has become very difficult, you know, equipment selection can be a critical path. So sometimes the use of AC current limiting device fuses can help me save a little bit of cost on my equipment ratings by making sure I have these devices in place, and I can use graphs like this provided by the current limiting fuse manufacturers to help select the fuse and then select any equipment that's downstream of that fuse. But this all depends on the idea that we have we have these constants in place that exist for AC systems that don't exist for the DC systems. So like Chris mentioned earlier in the presentation, DC systems are heavily based on site specifics. So when you look at DC rise, it's controlled by the L over R of a circuit. LRC if you want to be specific, but there's much more inductance than capacitance generally in the DC systems of BESS applications. There is a capacitor on the inverter that we take into account, but generally is dominated by the inductance of the system. And the inductance of the system comes from the cabling specifically. So we're going to parallel in series a number of these batteries together. Generally, you'll series the batteries into a rack. That rack will have the specified DC system voltage that you're looking for at the top of the rack, where you connect in your parallel cables that go to your inverter. But as we go after bigger and longer duration BESS batteries, the more batteries we're going to be connecting into these inverters, the worse this problem gets. But what we're doing is the more inductance that we throw into the system, the slower the DC rise will be. The less the inductance, the faster your DC rise will be. And what will happen is every battery application that we worked on has been very, very unique in this regard. So even though we can calculate it for an example battery here, we'll build another battery in another location with slightly different specifications, maybe different batteries. The site specifics of where the transformer is in relation to, where the inverter to the battery containers is all relevant. So it needs to be modeled specifically every time. So what we can do is we can model that in a program called EMTP-RV. This is a transient program that can model the LRC of the circuit, take into account all those factors. And what we're going to do once we model this, we can take the fast acting fuses, these current limiting fuses in the DC system, and compare that DC rise to what the fuse itself is going to trip at based on the available energy through that fuse. And we see the race. And just like any race, one side's going to win, one side's going to lose. If that fuse can run and burn out faster than the prospective DC fault current, we can have an application where the actual DC fault current can be much, much less than the prospective fault current, and we can see a lot of benefit to both equipment ratings and arc flash performance. However, if the fuse is slightly slower than the DC rise, then we have to use this prospective currents, which, as Chris mentioned and showed earlier in his presentation, can be substantial and significant. So this graph that we're looking at right here, I'll flip back real quick. We'll just wrap up. This had a prospective fault current, I think, of 185 kA. And what we found is this particular fuse and the L over R combination of the circuit, our fuses were blowing at approximately 15 kA. That's that top right value you see there. It's about 14 and change. I know the text is very small. I apologize for that. But that's where we found that our fuse was blowing on this DC curve. So in this case, this particular case, the fuse was much faster than the prospective fault current. But based on our experience, that is not always the case. And sometimes the DC prospective fault current rise is faster than the fuses. All right, so what we wanted to do is kind of do a one-to-one comparison. This is a nice analysis to kind of show, okay, what is the prospective fault current? And in this case, what happened when we put in these fast-acting fuses? So if we didn't have the ability to have these fast-acting current-limiting fuses, we would have to use prospective fault current. And mind you, arc flash is generally guided by an I²T function. Now, it's mitigated a bit by other factors, but in general, that's true. So what we find is we're knocking our current from a perspective of 125 kA at some of these applications down to the 15 kA we find with that DC transient analysis that we performed. So what you can see is the direct effect of the arc flash reduction from doing the DC analysis. So in this case, the DC arc flash wasn't terrible. You know, for those of us that work in arc flash, anything under 8 cals is generally, you can live with that and work with that because you'll be wearing reasonable amounts of PPE. But what we can see is by doing this DC transient analysis, we take it from having to wear PPE, like an arc flash rated PPE, to not requiring that at all by seeing that our arc flash basically goes to null. You know, so going to a 0.02 incident energy level, that's much less than a that you can work typical work clothes there because it's below a category 0 level. What we can see though is even though we were able to highly mitigate the DC arc flash in a number of areas, that also implies that we have protection in fuses of those areas. What we do see at the bottom here is that at the top of the battery stack, where there, like Chris mentioned earlier, there are no protective devices to clear faults. DC analysis, the transient analysis, does us no good because there isn't a protective device to clear the fault. Therefore, we're stuck using the IEEE 1584 maximum clearing time, which right now is at 2 seconds. And we can see that our arc flash levels here for this particular example are incredibly high. And anything that's over 30 cals is something of concern. Over 40 cals, most of the time we would not recommend working on energized. And then back to Chris's point, you can never really de-energize lithium-ion battery energy storage systems. So even at 0% charge, those batteries still contain about 80% of their total energy. So this is a major issue on how workers are going to be able to work on equipment. But I don't like to bring a problem without bringing a solution. So let's talk a little bit about some solutions. So one way that we can help mitigate this from this over 40 cal situation that we have is add some protective devices. Battery applications that are built today are when you have them, it's a series and a parallel combination. So you will series the batteries together to get to your total maximum DC voltage that's desired. Generally, battery cells themselves are approximately 40 to 60 volts. And as you series them together, you increase the voltage to your desired level, generally somewhere between 800 and 1500 volts DC. When these batteries are series together, generally it's done with bus bar that connects the positive to positive and negative to negative to get that series connection that you're looking for to increase the DC voltage. However, by replacing those bus bars with fusible links, you can have a protective device that would now separate all the prior battery modules from where the fault location is in a relatively fast manner. And by doing that, you can significantly reduce that clearing time and significantly improve your arc flash performance. So so here's an example on the same example. If we were to use these fusible links between the battery modules, we could take a arc flash hazard level that's over 40 cals, which requires the full suit that has a rating of that same rating or higher, and reduce it down to a much more manageable level. So what we can find is by putting fusible links here with some calculation, we found that we can knock that 40 cal arc flash hazard level, I think it was about 45 was the actual calculated value, down to just under 4 cals. And the nice thing about knocking it down to 4 cals is that's a very reasonable amount of PPE to be worn in the field. So that is very helpful. And the other concern with working with batteries is if you have the doors on the outside, at least you have the ability to escape. But if you're working inside these containers, the idea of you can escape a fault within 2 seconds may not be actually reasonable and possible. So if that's the application where you're inside the container and there's not a clear and easy escape route, then it's much more important to be thinking about this. Yep, and the reason this works so well is what you're doing is these fusible links are separating the other batteries. You may have anywhere between 8 and 20 battery cells that are series together. In this way, you only have to deal with the energy output, the full energy discharge of the one cell where the fault location is. And what you'll find too is since you don't have all those cells behind you, your total system voltage drops significantly. So even though your fault current is high, your system voltage will drop from your DC operating voltage of somewhere between 800 volts and 1500 volts down to the cell voltage, which is typically between 40 and 60 volts. So that greatly increases your arc flash performance. So with that rounds out our presentation. So we'll open the floor for questions and see what you guys have.
Thank you, Ian and Chris. Really great stuff here. Just a few reminders while we wait for a few more questions to come in. Remember, our next webinar is still to be announced and decided on the date, but it will be going over IEC 61850 about the standards defining communication protocols for intelligent electronic devices and electronic substations. Also with your PDH, make sure you keep an eye on your email for the certificate and an email from us. The email from us should also contain a link to a rewatch on-demand version of this presentation for you to share with any colleagues of yours who weren't able to come or those who you think might find it interesting. And then I think that is it for that. Also at the very end, there's also a survey. Let us know how we did. And if you have any questions, comments, or ideas for future webinars, something you might be interested in, you can leave that information there. With that said, I will read off these questions, and Chris and Ian, you can take turns or decide who you feel is the best to answer. We can go from there. So, all right, here we go. So the first question is, what is the purpose to do arc flash on BESS equipment? No one works on BESS equipment live. The system is built to shut down if someone opens a door to access BESS equipment. Isn't it sufficient to place a danger label on all BESS DC equipment and not allow anyone to work on it live?
So I think I'll take this one, Chris, if that's okay. So that gets into the characteristics of lithium-ion batteries. So even if so what does it mean to turn off? That means that the batteries may not be charging or discharging during the operation time, but the battery cells themselves will have a state of charge. Just like your cell phone, it'll be at 100% or 0%. But say, for example, you were going to work on these batteries after the batteries have been fully discharged at 0% state of charge. That battery, because of the lithium-ion technology that we're using in utility scale applications today, that battery itself will have 60 to 80% of its total capable charge. Lithium-ion batteries operate at the very top end of their charge range, and that's how they discharge. So it's not like going back to a typical lead-acid battery or a NiCad battery, that when that battery is close to its 0% state of charge, there's very little energy inside that battery. Even when lithium-ion batteries are fully discharged as far as 0% state of charge, they still have between 60 and 80% of that energy still captured in that battery. That's just how it works. So the batteries are never, ever truly discharged. And even if you opened every single battery cell away from the network, so we disconnected all the parallel operations, which generally are done with contactors, you still have that battery series stack energy available And that's the major arc flash concern that I was just speaking about, of 45 cals without fusible links. So to that comment, the DC, when you're working on a battery energy storage system, the batteries are never ever fully discharged, not from when they arrive from the manufacturer to the day that they're last used. So you can never truly turn them off. Even if you open the contactors and separate them from all the other batteries, there's still a major arc flash concern at that location.
Thank you, Ian. We will go to the next question is what type of fusing is used for DC circuits?
Chris, did you want to handle this one or?
I guess it really depends on what the question's really getting at. So DC circuits are real similar fuses to AC. They're just much, much faster and usually a little bit higher, well, maybe a lot higher rating so that they can handle the fault current, but there's still just a regular fuse that when it gets too hot, it burns. It just burns much faster. I'm not sure if that answered the question or not, though.
Yeah, to that point, if you look at some of the manufacturer spec sheets, they'll give you a little bit more information on that. And then you could look back to that list of just devices that we're familiar with as an example. But physically what these look like, they look like your traditional fuse. So the string fuses are generally, 6 to 8 inches long, approximately 1 inch diameter, with bus bar on either end, like you'd see in a typical AC fuse, but they're just designed to be for this application. The combiner fuses can be much larger, so those can be up to say 18 to 24 inches long, with diameters approximately 3 to 4 inches, mostly because they're rated to handle larger amounts of fault current. So it just depends a bit from manufacturer to manufacturer. And you can, if you look at the manufacturer nameplates, they'll tell you a little bit more about the construction, like the physical construction and the materials used inside the fuses to achieve some of the engineering specifications that we're talking about, this fast clearing time that we focused on here today.
Thank you, Ian and Chris. The next question asks, how are you modeling current limiting fuses in ETAP?
That's kind of where we get into the transient analysis. ETAP, I think it does do the current limiting fuse analysis, but it isn't very good at it with the DC side. So we usually just look at the steady state fault current in the ETAP to do the analysis. And if we want to go beyond that, we'll open up a program that's a little better at it, like the EMTP.
Yeah, so that gets to that point that every DC circuit is different. So ETAP can model current limiting fuses in an AC world, but ETAP is not smart enough to do a DC transient analysis, looking at system inductance to be able to see how fast a current limiting fuse would actually operate. So current limiting fuses in ETAP are pretty well modeled in the AC world, but if we're going to start looking at the DC world, we need to move to other types of analysis. And that's where we example that EMTP-RV analysis that we looked at the specifics of our DC application.
Yeah, in ETAP, we do model like the resistance of the fuses and the resistance and inductance of all the cables, but that's just for steady state analysis. We don't usually do the transient in ETAP.
Yeah, agreed.
Thank you. Here's the next question. Talking about mentioning conservative results, asking what method are you citing that is giving the conservative results?
Chris, you about that? That was on your slides, I think, talking about
if we're talking about the DC results, that's all the formula from NFPA 70E. And that's kind of the same formula. I think that's a pretty standard formula for DC side. I don't think there's too many other methods for that. But how you come up with a short circuit current to put into that formula depends on whether you're doing the steady state or the transient analysis to get a lower fault current. So it's going to be
the question was aimed at the conservative results on the AC side. So Chris, can you flip your slides back? I think that was like slide 7 or 8. Where we were looking at the different calculation methods. Now, when it comes up, there we go. Yep. So when it comes to low voltage, that's 15 kV and below. 1584 is the go-to for the industry. So there is one method. I wouldn't say that method is conservative. That is the industry standard method. When you get above 15 kV, there there is a lot of discussion, and there's been no IEEE based empirical study to look at higher voltage arc flash calculations, but there's been a lot of industry standard studies that are accepted out there. And this graphic that we have is a good example of that. So these are kind of the industry standard methods for calculating medium voltage arc flash. So when we looked earlier at our example, we talked about some medium voltage conservative results. That's because the IEEE method is given by this Lee method result. The Lee method, as you can see by the graphic, can be sometimes double or even triple of what the other accepted medium voltage arc flash calculation methods are using empirical data. So a lot of times in the industry, we may use one of these other methods, these industry accepted methods for calculating medium voltage arc flash specifically. But please note that the medium voltage arc flash generally isn't the major concern here. The major concern on the AC side is on the inverter terminals or the transformer low sides, which are low voltage, which are calculated with the IEEE 1584 methods, and the DC methods, which are calculated with NFPA 70E.
Oh, thank you, Ian. Thank you, Chris. A couple more questions came in, and we still have time for that. Let's go to, are you accounting for current limiting effects of CLF fuses?
So yes, on the AC side. On the DC side, that's where we do the transient analysis and we look at the effects of those CLF fuses. So I think, so Chris, if you go to your example, even where we weren't seeing any pickup on the AC for the transformer secondary fault locations that were showing up around 100 cals, that's accounting for the action of those CLF fuses. The CLF fuses, even though they're supposed to be a current limiting fuse, they still weren't fast enough to clear that low side fault. That seems a little counterintuitive, but that's what the analysis shows on this particular example. A lot of fuses will clear. What ends up happening when you're looking at a transformer low side fault is that fault current is reflected through the high side through the turns ratio of the transformer. So when you have a high medium voltage and a low voltage, there's a lot of transformer turns there, and that current can be divided by 30 or 60 times. So that CLF fuse may operate very quickly for a medium voltage fault, but when it sees a low voltage fault reflected through that transformer, that current is significantly lower. And because of that low fault current, it takes a long time for those fuses to burn or even pick up. Sometimes it's below the pickup value of the fuses themselves, which can create these very long clearing times. This is a kind of a known AC arc flash problem. It's seen across the entire industry and a lot in industrial applications where they have relatively high voltage connections to very large station transformers.
Yeah, so an ETAP is showing 100 cals at the low side because the fuse just doesn't pick up at all for a low side fault.
Yep, and that's modeling the CLF fuse that is in place here.
So
current limiting fuses don't really work unless it actually exceeds the value of the fuse in the first place. So
let's move to the conversation on cost. When we're talking about these sort of preparations to protect for arc flash, what kind of extra cost could someone expect to incur?
So I would say that the earlier engineering can take a look at things and help direct design. We can keep costs minimal. A lot of times is if we specify the right equipment the first time, then costs are minimal. It's just making sure that we have the correct equipment in place. We're not seeing like very significant changes between one type of DC fuse to another. It all seems to be pretty competitive, driven by market forces. So it's not like these DC application fuses are 5 times more expensive than an AC application fuse. They're all, as far as my experience is, they're all generally about the same. The biggest thing is if you buy one set of fuses and find out later in the project that they're not going to work, that's where costs can get substantial because you're having to buy everything twice, right? So my advice when it comes to cost is get engineering involved as early as possible in the procurement process. And that may be earlier than normal based on the current situation with procurement across the industry. But we can do preliminary calculations for examples. Even if it's not the full defined total build out of a site, we can probably get something that's pretty close and help find equipment with the appropriate ratings and the appropriate specifications early for helping with procurement and keeping costs managed.
Thank you, Ian. Great answer. Talking about purchasing, procurement, manufacturers, another question along that line, is the fusible link solution that was proposed something that must be implemented by the manufacturer, or can it be retrofitted?
Good point. I believe you could do it either way. Most of the time when you're buying batteries and you're buying batteries for a BESS application, you're going to be working with the equipment manufacturer, and there's going to be warranties tied to their equipment. So talking with the manufacturer about what your specifications and needs are early, and especially talking about the fusible link portion of that, they can include them at the factory, and the batteries usually come separate, but they'll have an assembly process from the factory generally. And that would be part of their warranty, which would be nice to have that there. If this is an older application or an in-flight project where this wasn't included, the bus bar for the batteries are generally pretty easy to get to. So it's not an unreasonable thing to add fusible links after the fact. But you want to check with your battery manufacturer about methodology and warranty impacts. I wouldn't expect there would be any warranty impacts. If anything, you're making the system safer. However, it's definitely a conversation that would be important to have.
Mm-hmm. Great.
And if you speak with the manufacturer, you can be 100% certain coming from the factory that it'll fit. If it's tight quarters, it could be that it won't fit later in the design. Hopefully you can make it fit, but it's guaranteed if you get it from the manufacturer.
Yeah, agreed.
Wonderful. Great question. Great answer. We have one more question here. It's going to be, okay. Which year of the NFPA 70E are you using to make the DCIE calculations?
I believe 2018 is the most current. We typically, when we start a project, we'll look up whatever the most current is. If there's any changes, we'll use that. And currently, I think it's 2018.
Yeah, it depends a little bit sometimes too, state by state. I think some states have full adoption, so you see that commonly with the NEC code. They'll adopt a certain version and they'll move to the new version after it's been vetted. So it'll depend project to project, state to state a little bit, but in general, we like to use the latest and greatest versions of any standard.
Yeah. And some clients will ask us to use a specific version as well, because that's what they have in their standards.
Yeah, and sometimes with a contract, when we work with our partners to bid on a battery project, we will specify standards as part of that bid. If the project is delayed, we may have to roll back to an older standard because that's what the bid was based on. So there's sometimes that can come on, but just as a general rule, we try to use the most current version of any standard when we perform engineering analysis. Yeah, I think there's a 2021 that's on the way here for NFPA 70 too. So
wonderful. Thank you, Ian. Thank you, Chris. Your knowledge is, I just thought this was great. Good time, really good time. Great presentation. Thank you very much. I appreciate it, as I'm sure the rest of our audience does as well. So thank you all for joining us today. Again, my name is Del Belcher, Marketing Manager at Commonwealth Associates. We look forward to having these conversations further with you. When you do your exit survey, feel free to leave any other notes or questions, and we can try to get back to you offline or through email. We'd love to do that. Remember, we are always doing a webinar about one a month, so stay tuned to our LinkedIn and your email for information on when those are happening. And your PDH information will be coming after this webinar is over through your email, as well as a link to a recording of this presentation. So you can always share that with someone else or watch it over and over again, because it was just such a fun time, With that said, I bid you all farewell for today. Have a wonderful Thursday, and thank you all for participating. And again, Chris, Ian, thank you very much.
thanks everyone. Have a great day.